So as you know, we've discussed what limits are. Just the basic, right? Just an intro. And now we're gonna see what are the techniques to finding limits, okay? So it's actually quite simple. So we learned there's 3 ways to find limits, right? If we had a calculator, we'd graph it. We can possibly find it by graphing. We can use a table on our calculator, or we can do it analytically, right? Okay, well, we're gonna teach you some techniques that use analytics to actually find limits, okay? So in 12.1, the limits were easy to find, right? They were pretty easy, and we discussed like what it means when you have 0 over 0 or infinity over infinity. But they were basically well-behaved functions, right? Most of them, okay? But now we're going to try something like this, where it's not so well-behaved. Then what should I do? Okay? So like, for example, here, we're trying to find the limit of this function, x squared plus x minus 6 over x plus 3, as x approaches negative 3. Now, you're right, you can always try direct substitution, right? And you saw that most cases when you did your homework last night that it works, okay? But let's see. If we try negative 3, here, if we do f of negative 3 here, what do you get? You get 9 minus 3 minus 6 all over negative 3 plus 3. You're like, oh, I get 0 over 0. And we discussed what 0 over 0 would tell us. So you're right. You remember 0 over anything is okay, but you remember that something divided into 0 is no way, right? But what about 0 over 0? That would be like a ooh. Okay? So you're like, that's what we call indeterminate. We can't really say much. Okay? It's not D&E, but we can say it's not a determinate form, so indeterminate form. Okay? We can't use this method of direct substitution to actually find limits. So what do we do? So this leads us to our first method, which is called the technique 1. Dun, 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 dun. We're going to try, okay, well, we could use our old methods, right? Our old methods are like this, right? We can take this, and we can graph it, and we can use a table. So go ahead and punch this into your calculator and see what you get for the values, okay? You plugged it in, you set your calculator up, and did you get something like this? Check, 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 okay? Yeah, okay. So remember, when you're finding limit, it doesn't matter what happens at negative 3. It matters as it approaches negative 3. So did you guys get something like this? Okay, as it's getting closer and closer to negative 3, what's happening? What do you notice? You're right. The limit, actually, we'll just write it here. Limit is what? Negative 5. Good job. Okay, it's negative 5. Okay. Oh, so it's not undefined. Because remember, at this value, you're right. It's undefined. But we don't care about that, right? Okay, so you're right. The limit of f of x as x approaches negative 3 is negative 5. That's our answer. And of course, we can check that with our graph. So if you sketched it, you would have seen that there was this little hole there. There's a hole there. Okay, and that was negative 5. As it approaches from the right and from the left, negative 3. Okay? All right. But that's graph and table. Now let's do it analytically, because there is a way, ladies and gentlemen, that you might have not known to find it. And the first technique that we're going to talk about is called the dividing out technique. Okay? Now let's find the limit as x approaches negative 3 of this function here. So I think you kind of remember, when you were graphing this rational function, do you remember what you guys used to do? You're right. What the factor, right? You first what the factor, and you haya, which means you factor it out, right? If you didn't have algebra 2 with me, then you wouldn't know what I'm talking about. So you're thinking I'm pretty crazy. So you what the factor this sucker, right? And you're like, haya, because you notice that you could, so you see how I'm writing this all the way out too? I do that every time. Right? So you're like, oh, I'm left with x minus 2. Ooh. So now you guys, look what you do. Now you substitute. So once you've factored out, and we used to call this, you're right, the whole. Remember, have a whole. Remember how you used to go, oh, let's find the have, horizontal as, vertical as, and let's find holes, right? That kind of guided you in graphing, and that's what we're doing. It's discontinuous at the whole. But the whole, it's the actual what we're looking for, okay? So when you substitute in here, what do you get? You get negative 3 minus 2, and you're right. You get negative 5. Therefore, the limit as x approaches negative 3 of this function is negative 5, as we suspected, okay? Great. So now you try one, okay? Now you try one with the dividing out method, because you're going to realize this example, second example here that I'm going to show you, you're like, if I plug in a 1 here, you know you get a 0 here, so no good, right? Because you'll get ooh. When you do direct substitution, you get ooh. So you're like, ooh means what? Ooh means, I better do something, okay? So go ahead and try the divide out method. Div out method. Oops. Div out method, okay? Try that on your own. All right, welcome back, okay? Hopefully you got something like this because you factored, and everybody here knows what the factor, right? So you factored by grouping, and you should have got something like this. Yeah, give yourself a thumbs up if you got that, all right? Now you go, hi-ya! You do the karate chops, and you should have got something like 1 over x squared plus 1. Now at this stage, what do? Now you substitute. Okay, so you should have got 1 over 1 plus 1, which is 1/2. Okay, so that is the limit. So limit of this sucker here is actually, remember, we don't care what happens at 1. We care what it's approaching from left or to the right. So it's 1/2. Okay, now if you don't believe me, let's actually verify this one, okay? So we're going to verify the last one, so it looks like this, okay? When you graph it, it should have looked something like this. Did it look like that? Try graphing it, okay? All right, you see, as it's approaching positive 1 from the left or to the right, it's going to about 1/2. All right, now, what do you think? You're right, there's more methods for you, okay? I don't just give you one method, okay? Now, technique 2 is called rationalizing technique. So you have the div out technique, and now you have the rationalizing technique. So look at this one, okay? Okay, you're like, if I plug in a 0 here, you get 1 minus 1, which is 0, and 0 over 0. Remember, again, you get, 0 over 0, right? That means, what should I do? You know it's indeterminate, therefore you're going to try a different method. Now, this method is called rationalizing technique, so here's what you do first, okay? All right, we're ready to start. So this is weird, because the rational is on the numerator, right? So here's what you do. You're going to take this guy. I'm going to go limit as x approaches 0. And you know how, actually, you know what? I won't write this. Just, let's do this way. So you see how we have x plus 1 minus 1? You remember how you used to rationalize the denominator? Well, now you're going to rationalize kind of the numerator. So what's the conjugate of this guy? Right? Remember, this guy's a package, so you're right. You're going to rationalize it by going x plus 1 square root plus 1. Remember, a plus, a minus b, a plus b, right? Same thing to the numerator and denominator. So here's what you get. Okay, so what happens when you get this? A squared minus b squared, so you're right, it's x plus 1 minus 1 all over, what do you guys get here? X, this becomes a little bit, I would just leave it alone, and later you're going to know when should I multiply it and when should I not, right? Okay, so you got something like that. Okay, so let's simplify that, and you'll get something like x over x square root of x plus 1 plus 1. Okay, and you're like, hi-ya! So you're actually left with this. Right? Yay, okay. So now, of course, we have to state that x does not equal 0, okay? Because remember, x does not equal 0 here, okay? All right, okay, so now we try to find the limit. So we've rationalized this function here. So now let's actually find the limit, okay? As x approaches 0, what is the, so we could rewrite this, the whole problem, okay? Now let's find the limit. So limit as x approaches 0 is going to become 1 over square root of x plus 1, because we've already rationalized it, right? So we get this. Now direct substitute. Okay, you see how direct substitute is almost always in play. So you get 1 over 0 plus 1 plus 0. 1 plus 1. Then you're actually left with 1 over 2. So, what's the limit of this guy? It's actually 1 over 2. So you see that? It's called a rationalized technique because we rationalize the numerator. And now we direct substitute. and then we actually find our limit. Well, if you don't believe me, let's checky, okay? So always check with the graph. So I'm going to check for you. Let's verify that last one, right? Let's verify that last one. It should look like this. Here's your function, this here, when you graph it, and you're looking for as the limit approaches, what was it? As it approaches 0. So you can see as it's coming from the left side, from the right side, it reaches a half, okay? So let's go ahead and do the next one. At times when the limit approaches different values from each side, we can look at each limit separately, which is called one-sided limit. What does that mean, okay? So we're going to study that. So as I've told you, right, limit, take a look at this, limit of f of x as x approaches c from the left. This little minus on the superscript, it's actually from the left. It's equal to limit L sub 1. Or we can say f of x as it approaches L sub 1 as x approaches c from the left. So this one is limit as x approaches c from the right. That's what the positive sign means. Is L sub 2, which is the limit of this guy coming from the left and coming from the right. So you'll see what we're going to do with this. So let's try some, okay? So let's check example 4. All right, example 4. Here we go. Example 4 looks like this. Find the limit as x approaches 0 from the left and the limit as x approaches 0 from the right. You see how we separated the instructions, right? Okay? And again, you know that x is undefined at 0, so you know what's going to happen with this, right? Okay? So you know we can't just use direct substitution is what I'm trying to prove to you. Okay? All right, now, let's do this. Okay, so we can look at the graph, but let's actually do it by hand first, okay? So f of x is equal to negative 2 for all x values less than 0. Do you agree with that? So you see how this is absolute value? So if x was a negative, if x is negative, right? When you solve this, don't you get a negative 2 every time because the x's cancel out? Okay? So limit as x approaches 0 from the left is going to be, let's represent this as absolute value of 2x equals negative 2. Okay? From the left, okay? How about limit as x approaches 0 from the right? And you have absolute value of 2x over x, that's going to equal positive 2 for the same reason, right? Because when you have positive values here, it's going to become 2 no matter what. Okay? Okay. So this is the limit as it's coming from the left towards 0. And this is the limit as it comes from the right to 0 of this function. And let's actually take a look at the graph and see if it makes sense, okay? Coming from the left, coming from the right, and they're different, okay? And we're not asking you for the limit of this whole function with these given conditions. We're just asking you, in this case, from the left and from the right separately, okay? All right, let's try another one. Finally, let's try this one. Let's read over this. If f is a function and c and l are real numbers, the limit of f of x as x approaches c is going to be the limit L. This is no different than what I introduced to you from 12.1, okay, as we were discovering limits, okay? So here we go. If and only if both the left and the right limits exist and equal to L. That's what we explained that in 12. Remember that? So we're going to try this one, okay? Find the limit of f of x as x approaches 1. Okay, and we're given these piecewise functions, right? There's 2 given these conditions, okay? All right, so why don't you guys go out and graph that right now? By hand, okay? You know exactly what this one is a linear, this one is a, you can see it's a quadratic, okay? All right, so let's actually see how we can work this out. So we're going to go x less than 1 first. Limit, less than 1 just means it comes from the left, right? Because everything less than 1. So limit of as x approaches 1 from the left. So f of x is going to equal limit x approaches negative 1 from the left. It's going to be 4 minus x, correct? Okay, so let's actually find that. It's 4 minus 1. We use direct substitution and we get 3. So direct substitute, okay? Okay, that's going to be 3. Okay, how about from the right? X is greater than 1, right? That means its limit as x approaches 1 from the right. So I'm going to go 4x minus x squared, okay? And again, let's try direct substitution because that doesn't cause any problems. And it's going to be 4 times, oh, I'm sorry, I just want to get to the next step, okay? So it's 4 times 1 minus 1 squared, right? So which is going to be 3. So now, as it comes from the left, it's 3. As it comes from the right, it's 3. So what can we say about the limit? So we say limit as x approaches 1 is going to be 3, okay? And we can verify that from this graph here, okay? All right, try that, okay? All right. Next, there's a special something that I want to show you, okay? Because I feel like when you see it, you're going to be a little bit scared of it. But because I don't want you to be scared because it's really nothing, I want to kind of introduce it to you before you see it, okay? All right, let's try this. So they want us to find the limit, okay, of, solid right here, a limit as h approaches 0. I mean, we could use any variable, right, of this function here, given, so find this, given, okay, f of x is equal to square root of x. Now, this is called the famous difference quotient, which we're going to talk more about in the next section. But for now, all you have to worry about is, how do I deal with this? What do I do, okay? So here's what you're going to do with this. You're going to just find the limit. So what do? You're going to plug it in, okay? So square root of x, right? So limit as h approaches 0, well, f of x plus h. So what are you going to do? You're going to, every time you see an x, you're going to plus an f of x plus h. So you're going to go square root of x plus h minus f of x is our square root of x. And what's our h? Our h is just h. Duh, okay? Now, well, we can't just plug in a 0 because you know it's going to become what? Square root of x, and h? What? That doesn't do us anything, okay? Because remember, ultimately, when it's approaching h, right, a constant, we want it to approach something in terms of an x at least, right? So here, what do? You're right. Think about the techniques that we learned, rationalizing method, right? So we're going to rationalize this sucker by multiplying this by x plus h plus square root of x plus h square root of plus square root of x. And when we do that, we get this. Limit as h approaches 0, we get x plus h minus x. Make sure you understand this algebra part of it. And this is going to be h times square root of x. I'll just write x first. Doesn't matter, but okay, fine. I'll just go in order just so I don't confuse you, if any. Okay, so I get that. But now what's going on here? Oh, so hiya, right? The x's cancel out. So you're left with, you're right. Okay, h over h times square root of x plus h plus square root of x. And you're like, hiya! You're right. So you get limit as h approaches 0, 1 over square root of x plus h plus square root of x. Now, there's not going to be any problems here if I directly substitute for 0, right? So let's directly substitute, so direct substitution, right? And here, you're going to direct substitute for h. So when I do that, I get 1 over square root of x. I guess I should just show this. Okay, and you know what you guys get? You get 2 square root of x. So you get this. So 1 over x, square root of x plus 0, because h is 0, and square root of x. So you get the limit is this. This is the limit. And you'll see what this really means later. It's going to be so cool. So limit of, as h approaches 0, of our given function, square root of x, our given f of x is going to be 1 over 2 root x. And you'll see what this beautiful thing means. So try that for homework, okay? Good luck. Bye.